5.3. Connecting f prime and f double prime with the graph of f. Nathan, can you turn the air down like a little bit more? I'm still like croaking up here.
Wait.
That's fine.
Okay.
You might have to turn it. Yeah.
It's like blowing hot air this time.
Oh no, I just turned it down a little bit when I came in, but it just hasn't. I don't know. This sweater's really hot. I might have to take it off.
That's comfortable for you.
Okay. Well, I don't know if y'all are hot or cold, but
I'm frigid.
are you really?
I'm a little cold.
I thought it was kind of warm.
Yeah, I thought it was kind of warm too.
I feel fine.
My hair is also down, so that might be part of it. Okay. Anyways. All right. Theorem. First derivative test. For local extrema. The following test applies to a continuous function f of x at a critical point C. One, if f prime changes signs from positive to negative at C, and this is in parentheses, f prime is greater than 0 for x less than C, and f prime is less than 0 for x greater than C, then f has a local max value at C, a little baby graph to help us understand. Alright, so this little line here is C. So then on this side, f prime is greater than 0. On this side, f prime is less than 0. So we would have a local max at each of those points there.
I still don't understand the illustration. I don't really understand the graph.
So C is basically like stellar critical point. And then it's saying that this is the graph of the derivative.
Oh.
No, wait a minute. Maybe? Maybe not. Yeah, this is the graph of the derivative. So in this one, over here, f prime of c is equal to 0 because it like stops and turns around. It's like when we were like, talking about like throwing a ball up in the air, there's like a moment where it stops. That's basically like, that would be like the max point of that is where it's stopping. So that one would be equal to 0. But this one, because we have a cusp, the derivative is undefined. So f prime of c is undefined. So it's just saying that the derivative is greater than 0 on the left side and less than 0 on the right side. Basically, it's going down, so it's negative or positive. All right, the second option, if f prime changes sign from negative to positive at c, the f prime is less than 0 for x less than c, and f prime is greater than 0 for x greater than c, then f has a local min value at c. So basically, I'm just going to reverse these graphs, flip them upside down. What? I don't know. I didn't draw an arrow. I just...
It decided to get an arrow again.
Okay, we're just going to just not fix it. And that one, it didn't do it. Okay. I guess it decided I needed an arrow. Who knows? All right, so again, this is going to be C. That's our critical point. It's almost lined up. Good enough. Nope, that is not what I want. Good enough. So on this side, f prime is less than 0. This side, f prime is greater than 0. So there is a local min there, and a local min there. But again, in this one, f prime of c is equal to 0. Over here, this time it's more of a corner, so f prime of c is undefined. Huh? Is this far enough, or do you mean go farther?
Oh, no, I just need to see something. You can go back.
Okay. Don't fall.
I'm bored.
What is calculus? Aren't those things, what is it called?
Backlit.
Aglets. I always forget the name.
You gotta sing the
But
Phineas
who's
and
the
Ferb
song?
song. A-G-L-E-T.
Balaclavas are island.
Huh?
I forget what balaclavas are island.
Yeah, ski masks.
I'm gonna forget what a balaclava
Ethan, do you know
is.
what a balaclava is?
Sweden.
Yeah.
You sporty people don't know.
I didn't know what it was. Only once he explained it did I realize what he was talking about.
Right, like.
Alright, we have a third option though.
If the sign doesn't change,
Did you read my notes?
definitely not.
If f prime does not change sign, at C, f prime has the same sign on both sides of C, which, makes sense. But it can be either way, like, can it be like positive the whole time or negative the whole time, doesn't matter. Then F has no local extreme value at C.
It's like one of those little birds you draw as a kid. And
Every time I draw,
still draw 'em. I'm not sure.
every time I don't draw that often anymore, but every time I draw one like a cusp graph, I always think of a bird because
Yeah.
that's pretty much always what they look like. So there is no extreme value. So I'm just going to write no extreme to shorten it. So in this first graph, f prime is greater than 0 on both sides. On the second one, f prime is less than 0 on both sides. But still, f prime of C is equal to 0 on the left one, but because that's a cusp on the right one, f prime of C is undefined. So far, we've primarily discussed, even for the amount of this chapter that we've done, we've primarily had max and min values in the middle of the graph, right? Other than we had a brief couple of problems where we had something at the endpoints, or like those graph pictures that we looked at where we said, well, there's a max value at that endpoint or whatever. But we need to address that because that does happen a decent amount, especially when we put a restriction on something. So I'm going to mix it up because I want to change colors just because I can. I'm tired of red. At the left endpoint A, if f prime is less than 0, or I'm going to put this in parentheses, f prime is greater than 0 for x greater than a, then f has a local max if we have the first option. The option that's in parentheses would give a min, so I'm just going to write it like that. Value at a. Did it again. All right, which thing do I have on this left graph?
That's it.
Yep. Local max over here. So the other one is A. Local min. And instead of this being C, this is A on this graph. And this means that F prime is less than 0 on this one. F prime is greater than 0 on this one. So those are at the left endpoint. So we're also going to do at the right endpoint A. Actually, let's do right endpoint B just so we don't get confused. If F prime is less than 0, or the other option, F prime is greater than 0 for X less than B, then F has a local min or max for the parentheses option value at B. This point now is at B. So what is the graph on the left? Local min, meaning that F prime is less than 0. The one on the right, local max. So F prime is greater than 0. All right, usually I pause there and we do examples, but I think I'm just going to go ahead and do all the notes, and then tomorrow we can just do all examples. Or
Okay.
wait, I was about to say tomorrow's Saturday. Tomorrow's Friday. How unfortunate.
Wait, so why is F prime less than 0 on the one side? Well, I don't know why.
Because it's a min, so it's going down. Or are you saying why are they different?
Yeah.
Because we're looking at...
That's a local max up there, but then F prime is less than 0, so it's confusing. Because then that max is F prime is greater than 0. Is it because the direction of the line?
Let me make sure I didn't write them backwards. Well, we're looking at B versus A.
Okay.
So the derivative graph itself, this is what we're talking about.
So is that, so like, okay.
So like technically these are the same graph, other than the endpoint that I'm looking at. This one I'm looking at the left endpoint. Down here I'm looking at the right endpoint.
So is it less than because like it's going down, but then that one's also less than because it's going down? Because it's a max. And that max is, the B max is under that.
Gonna be honest, I don't know why it's true. It just is.
So like how would I like know?
Well, it's based on the reason they're saying it is because it's what endpoint you're looking at
Okay.
for that particular situation. So like in the top one, we're looking at the left endpoint, and so we know at the left endpoint. Oh, you're saying how do you know what the derivative is less than 0 or greater
Yeah.
than 0? Well, there would be a value associated with it,
Okay.
like how we had like. I see what you're saying now. Like how we had, like we would say, well, the derivative is like equal to, like the derivative at the point is equal to this.
Okay.
If that's less than 0 on a left endpoint, then it's
I
that.
didn't know if it had to do with like whether it was a min or a max or like.
Well, it does, but it's a min or a max because of that, not the other way around. Yeah. I thought you just meant like, why is it that way? And I was like, I don't know.
No.
Gonna be honest, I don't know. The book just says that it's true.
The philosophy.
Every teacher I've ever had told me this was true, so I think when we start putting
The example.
numbers to it, it will help.
Yeah.
I'm usually better at seeing things once there's numbers in there, which is why I was like, well, it's whatever the derivative value is at that point would be less than 0, and it would, yeah, anyways, greater than 0, whatever. Oh, come back. All right, concavity.
Oh, yeah.
All right, and then we kind of got a definition the other day, but I'm going to give you the official book's definition just so you have it. The graph of a differentiable function is A, concave up on an open interval I, if y prime is increasing on I, and B, concave down. Find your pencil back there. On an open interval I, if y prime is decreasing
Makes sense.
on I. Can you guess what the test name is for this one?
The test of concavity.
Almost.
Concavitiness.
Concavity test. I think he said the test of concavityness or something.
I first said test of concavity.
So we've had a first derivative test, we have a second derivative test, now we have a concavity test. I thought he said, "Oh, please," and I was like, are you getting sassy back there?
Yeah.
What?
Maybe
Never.
that's-
Sassy
this
man.
is literally
Sometimes. You can be sassy too, Josh.
Oh, I'm always sassy, but we're
Oh.
not talking about it right
Okay.
now.
I'm sassy too.
When was the
Yeah,
last-
me too. Don't go back.
when was the last time I was sassy? I don't even know.
Like 5 seconds ago.
Really?
Yeah.
Wow.
That was all sass right there.
Wow.
Ethan, are you ever sassy?
Ethan's always sassy.
No, I'm not.
Yes, you are.
Yeah, that's it.
You just are. It's just a lifestyle.
Yeah.
You can't choose the sassiness. It chooses you.
All right, the graph of a twice differentiable function just means that you can take the second derivative
Oh,
of.
it doesn't mean you have to?
Well, we need it, but
Oh. Oh, man.
You can, but
so yes, we have to take the second derivative to be able to do this. Is A concave up on any interval where y double prime is greater than 0. So that just means whatever the value of the second derivative is, if it's greater than 0, it's concave up. So within a particular graph, it could change directions multiple times and switch from concave up to concave down and back to concave up. The way to test for it, though, is honestly, you'll appreciate it, I think, a lot more than the other stuff we've done.
Oh,
And it's concave down on any interval where y double prime is less than 0. So when we test this, we're basically going to make this little chart thing that you might remember having done last year, but obviously weren't doing it to test for concavity, but we had like values here, and I'm just going to use A and B, that were like zeros of our function. So it's going to be a similar thing here. It's going to be where the second derivative is 0 are going to be those values. And then what's going to happen is in here, we're going to pick a sign based on the function. So we're going to pick a number like
Oh.
over here. Like let's say this was 0 and 2 just to make this easy. Okay. So like if this was 0 and this was 2, I would choose the number over here like -1, and here I would choose 1, and in here I would choose 3, let's say. And I'm looking at the sign, and this is the critical part, in the second derivative. Okay, so we'll plug the number back into the second derivative and test, and then that will tell us if this point A is concave up or down, and then if this point B is concave up or down. So we may only have one, we may have multiple, it just depends.
I like this.
Okay? Well, the good news is it's not the only time we do something like this, but it's where it gets a little tricky because it can change. When we do the first derivative test, we actually do the same thing, except for it gets plugged into the first derivative. So concavity is plugged into the second derivative. So again, those numbers I wrote in green are just for reference of what that would look like. And then we would check sign, and then from there, that's where it's saying like where y double prime is greater than 0. So if it's positive, it's concave up. If it's negative in there, it's concave down. We don't care what the value is. We just care if it's positive or negative.
What did we use this with last year? 'Cause I remember doing it.
Solving equations, and inequalities.
Oh, okay. Yeah. Because I remember doing it. I just don't remember what section.
We like found the zeros, and then we figured out where it was. The thing asked for you to find the interval where the function is positive, negative, or 0. And then when we did them for inequalities, when we did them from rational functions, we had to tell also where it was undefined, because undefined wasn't included, but zeros were included. And then for inequalities, if it was like a greater than, then we were choosing positive, and if it was like greater than or equal to, we were choosing positive and 0 values. So yeah, that's what we did it for. We just did that, well, before Christmas, obviously, but not that long ago in there. All right. One more thing when it, maybe two more things when it comes to notes. I don't know. We already have the second derivative test written down, which, like I told you before, they teach you in this section, so we may not write it down again because you already have it.
Oh yeah. Wait, why do they teach it in this section when they're?
There's other ways to do it, but I think the second derivative test is easier, so I taught it to you early.
Okay.
Like, you don't need... Both methods work, so you might as well use the easier one, if that makes sense. There's other ways to do it, but I like this one better, so I just teach it early. All right, points of inflection. Definition: a point where the graph of the function has a tangent line and where the concavity changes is a point of inflection.
You said concavity line, or just
Where the concavity changes. Tangent line.
I can't. Somehow.
It's okay.
It's okay.
Hmm?
I almost died at lunch.
Wait. Why did you almost die English? Did I miss something?
The oatmeal.
Oh yeah, yeah. You both choked today. What the hell?
I almost died at lunch.
Yeah,
I'm like,
you
Quacka's
He almost died in oatmeal. Not died in.
I started
not died
crying.
in oatmeal, but
The
he
tears
died
were
in
running.
oatmeal.
That would be interesting. So with points of inflection, just so you kind of know what you're getting yourself into with that, you take the first derivative, then take the second derivative, and then we set it equal to 0 and solve, and then we take those numbers and we plug them back into the original to find the points of inflection.
Okay.
Now, we will typically test to make sure that concavity really did change, because sometimes it will stay positive or stay negative, and the concavity is not actually changing, and so then it's not a point of inflection. But anyways, it all goes together, but they break it up into pieces. So anyways, that's why sometimes I do it the way I teach it, where I do some notes, do some examples, do some notes, do some examples. But anyways, that's it for today. I think the bell's close to ringing, so